Alright, welcome back. I'll give time for folks to get notifications, and in the meantime, I'll spam Blue Sky and Mastodon. Blue Sky done. Mastodon done. Okay. So, if you followed yesterday, we had it spinning forever, so I did some annoying debugging and some print line debugging. Um, and found out that the here, for example, these values which were supposed to be the infinity norm, so the absolute value of the centered modules of values that were supposed to be 0, 1, or -1, were definitely not 0, 1, or -1. And I hunted it down with a few tests, initially thinking that the infinity norm was broken. It was not broken. And then realizing that the constants were broken. And I remember picking these constants from Python, doing exactly the same thing I did to generate the new correct ones. So who knows? I must have fat fingered something or misinterpreted the Python operator precedence, which would not be the first time. And it was just the wrong constant. Then the signature was not the same. Turns out there was also this. When it says the spec says divided by 4, they mean bit length divided by 4 becomes byte length. Supposedly because this is the collision strength, and for collisions to get a collision strength of 128, you need 256 bits. Yeah. Um, so, anyway, with those two bugs fixed, the tests pass. So we have a working implementation of key generation, public key generation, and deterministic signing. And randomized signing is basically the same. Instead of using zeros, you use a random value. We just don't have test vectors for it in whiteproof, which I think we're just going to, I'm just going to add a script that adds a few entries to, for the valid ones. It just adds a version with a random random string. Okay, so we got this far, and now it's time to implement verification. Let's start by looking at the external verify function. Simple enough. It just checks if the context is too long, which fair enough, and then it produces mu, the message representative, the same way as signing, and passes the public key and the message representative and the signature. Okay, nothing surprising in here. Internal takes a public key, encoded as a bystring, but actually we're going to do the parsing separately. A message M encoded as a bit string, no randomness is required, produces a boolean value. The expected lengths, yep. If an implementation can accept of any length, shall return false. If the thing has the wrong length, we return false. Fair enough. First extract the public random seed row and the compressed polynomial vector t1 from the public key. Then extract the signer's commitment hash, ch, response z, and hint h from the signature. The verifier may find that the hint was not properly byte encoded, in which case return false. Assuming the signature is successfully extracted from its byte encoded, verifier derives A from row, which we are actually going to do at key parsing time. This is generally a pattern that has worked very well for us, is parse, do all of the work you can in a key parsing step, generating an in-memory representation, then operate on that in-memory representation. As is done for key generation signing, creates a message representative mu by hashing the concatenation of tr, which is the hash of the public key pk, and the message m. The verifier then attempts to reconstruct the signer's commitment, which is w1, from the public key and the signature. In signing, it's computed by multiplying a and y. In verify, it is computed by getting ch and then doing this, which uses the high bits of t1, and then I think using the hint to go back from the approximation, which is this, to the non-approximated version, because remember that ML-DSA does this trick where it doesn't want to send the entire t vector, so instead it sends t1, and then for every signature it sends a small hint as to what the approximation broke. Essentially, it says, oh, did the approximation fail for this bit or that bit or that bit. Finally checks that the response Z and the signer's hint H are valid, and then they're constructed, checks that they're small. Weird to do this at the end. I kind of want to do this at the start, but I guess whatever. H contains no more than that many zero coefficients, same stuff we've done inside. And CH matches the representative, which, wait, how is that a check? Oh, we have to extract the CH from the signer. Yeah, I don't like the idea of doing all of this using the signers commitment and then only at the end. Oh, but that's because we don't have W1 when we start until the end. It's kind of scary that there is a line here at the end which checks that the hash of the message actually matches the stuff in the signature. And if you just forget this little part, you wrote something that all works, but the message can be anything. I bet that there's going to be vulnerabilities where somebody implements the whole spec, but not these few characters, and the result is broken. But I trust that we have whiteproof vectors for it. So, okay. Pretty clear. We need to decide what to put in our public key step. And this part doesn't depend on the signature. This part doesn't depend on the signature. This part does not depend on the signature, so we can pre-do all of this stuff and reuse it in case you're using the same public key to verify multiple signatures. Then this definitely depends on the signature because it depends on the message. This is the same sampling as we did when signing. And this multiplication by Z came from the signature. I wonder why we're not putting the entity of Z in the signature. Maybe because it wouldn't be small, and I think Z is picked to be small. Probably, yeah. And then the entity of C, which also comes from stuff in here. But the entity of T1 times 2 to the D instead depends only on the public key, so we can actually pre-compute this part. So we can store this instead of storing T1 because T1 is not used anywhere else. Okay, so let's make our public key structure. And we drop the thing where we were keeping the copy there. Let's see, type public key a struct. Row, which is going to be a sequence of by we can probably pick the largest possible signature. No, the largest possible public key. It's 2 kilobytes. It's gonna be fine. I guess we could calculate it. It said something about providing an algorithm to calculate it. Oh, it's this. It's 32 plus 32k times the bit length of that. What is the number of dropped bits from T, which is always 13. We can. It's probably useful if we have pkey encode open somewhere. Pkey encode and decode. Okay, so it's just raw, which is 32 bytes, and then k times I think 10. But also we implemented this. It's 10 bits times n, because each coefficient, times k. So it's going to be 32 plus max k times, it's not 20-bit coefficients, it's 10-bit coefficients, times 10 times 256 divided by 8. Comes out to 2592, which sounds right. 2592, yay! Uh, uh, okay. We're gonna need the parameters, that's for sure. Then we're gonna need row. Which is 32 bytes. Then we're gonna need a. Wait, we are not gonna need row, because row is only used to expand a. We're gonna need tr. And we're gonna need this. We're gonna call it t1, but it will actually be, so t1, 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 t1. Oh, it's just called that because I think it's a k-sized. Yeah, it's length k. So it's t1 times 2 to the d. Okay. We have two options. Recompute this every time we are asked for the public key from the private key, or pre-compute the, or include the public key. I think we should probably just include the public key. and remove the non-secret parts. Let's just embed public key. Maybe. What does RS say? What does everyone else do? So this one embeds it. This one embeds it. But here I ended up not embedding it and having a method. What does the method do? Returns a pointer to it. Let's see how ugly this makes the code. Because we're gonna have to change where we... Okay, this is not the worst. It's kind of wasteful to generate this T1 every time we generate a private key if we think the public key is not going to be used, because this is not needed to encode it. But I guess, would we care more? Performance of key generation which is not followed by a public key verification, or performance of multiple public key verifications in a row? Or we decouple the types and we don't actually use the public key struct inside the private key, and when asked we make a copy and a little bit of computation. Maybe that's the answer. That's not just a little bit of computation, because we're not keeping this row, we're not keeping t, the full t around, we're only keeping t0 around, because then that's what we use when signing. All right, for now, let's keep the full public key computed inside the private key, but let's not expose it. So if we decide later that we actually didn't want to do that, we can revert it. We need PK encode to be an appender. So let's do that. It was already an appender, so Easy enough. This way we can do priv.pub.row there. And we read it into tr. Okay. Let's add the private key method that returns the public key. And we can return a pointer because there's nothing that can change a private key after we used it, because we created it, because it's a completely opaque value. Just leaving breadcrumbs for if people complain about memory consumption. And then public key is going to need a bytes. Equal, sure. Which compares row. Yeah, that sounds right. And bytes. Which figures out correct the let's actually do the same thing here. Oh, wait. Equal should also check the parameters. Yeah. Because you could technically have the same seed. This one is more unlikely, but well. There. Okay. So I think we've computed everything in keygen, except, so we have row, yes. We have P, we have A, we have TR, we don't have T1. So let's do T1. Is there anything special about how T1 is? There's nothing special about T1, I think. T1 is just coded from there and multiplied by 2 to the D, which I think is just a shift and then a reduce, because I think it can overflow. I have this vague memory that how it's defined, it might overflow. So this is power 2 round low, which actually does the same work as power 2 round high. So maybe we should change that. So we're doing round low and round high separately. But we're doing them both, and it would be useful to have T0 and T1 so that we could... we have to figure out what types to give these. It's a little annoying because it was nice to just pass T into PK encode because those are actual ring elements instead of some weirdo values. Uh, yeah, I think we gotta redo this. Is there a test for this where we can check if... Wait, we have no test for that at all? Oof. Well, time to write one. Yikes. Okay, let's just merge them into power 2 round. Oh, round high is used, we said, for encode. Okay. Okay. And let's make it return high, low field element. All right, we combine them like this. And then to use them, we need to make both T0 and T1. In which order do they put them? T1, T0. And we need to invent a type for T1, which is probably make slice of n u in 16th of length k. Well, a slice of that. Let's rename this to W1, no, W0, and W1 instead is a yep. Actually, we can just use T1I here. And this can just be W. Okay. Annoying that we have to get out of the entity to do the rounding just to go back into the entity immediately after. But I think it's necessary. Okay, so this one instead will be just T1. We can drop this comment. I think these just go away. Yup. No, wait. Here we need to pass T1, which is a slice of n uint 16s, because these are the high bits. Okay. We would give a proper name to this type if we had to move it around more or store it, but we don't need to, so great. It's still broken. What is broken? Oh, we just need to add some pubs here. Okay. This is public key dot bytes. Same for the other two. Okay. If the tests still pass, we've refactored enough. Yes. Test still pass, so now we can write a better test for power to round. Because the first thing I want to know is if the high part shifted left by 13 ever overflows Q. So low here is a field element, so reconstructant needs to be to Montgomery of U in 13 high shifted field add. But to Montgomery needs. Let's call this T1. Let's call this T0. And we can just do high this part is not needed because if it's higher than that it will fail. All right, let's see. It passes. Okay, so that means that for all values of t1 from power 2 round, t1 shifted left by 13 is always uh, uh, lower than q, because that's the first check that Field to Montgomery does. Excellent. So where we need to compute t1 and tt'd, we said we need the entity of t1 times 2 to the d. So let's do that. Priv.pub dot t1 up to k for everything in t1. We make a ring element, and then we assign that ring element to the entity value of that. Yeah, and here, nope. Uh, uh, t1ij shift left by d, which is 13. Okay. And this should let us compute a valid. Yep. Yep. Okay, so this gives us t1. So now we've done t1, that expand a. We still need to do PK decode, but I'm kind of excited to do verification. So let's just keep going. We have all of the values in gray. So now we need sig decode. There's no way around that. So we go to wherever we implemented sig encode. Which is actually not too bad. And we pass signature and parameters, yes, and we return ch, yes, z, yes, h, yes, and an error, yes. Ch size is that, yep. Yep. So let's figure out the maximum size of a signature. A signature is plus secant code is applied to Z, which is uh, L, and each of them has at most log 2 of gamma 1 bits. Is that 13? That doesn't sound right. So secant code, it's doing a bit pack. And bit pack is either 18 or 9 or 20 because it's gamma 1 plus 1 because it's plus minus gamma 1 the range of values. So 1 plus log 2 of gamma 1 bits plus the hint, which is that times k. Right, and ch is so that max L times N times uh, plus 1 divided by 8 plus 80 times max k. Although, wait, that's not right, because this has to be the max this time k, and this one is 80 times 4, 320, 55 times 6, and 75 times 8. So actually 600 is the max. Let's see if we got it right. It comes out to 5144. Is that right? It is not. Okay, why is that? Is it times or is it plus? It's plus. Um, huh. So, okay. This is not working anymore. Oh, we need to decide how to expose the constants for the various sizes. I think we just have to hard code them. So let's do that. Public key size. I think we have various public key size types, like in, I think ED25519 maybe. I just want to use the same names. Public key size, private key size, signature size. So private key size is 32. It's the seed. Public key size 44 is 32 plus 4 times n times 10 divided by 8. 4, 5, and 7, yeah. And signature size instead is divided by 4. So 32. Well, let's write it out. Plus L, which is 4 times n times 17 plus 1 divided by 8 plus 80 plus 4. Those looks right. 4, 5, 7 are right. 17, 19, 19 is right. 80, 55, 75 is right, but this is the plus k, which is missing, which is 6 and 8. Okay. One, 3, 1, 2. 1, 9. Oh, this one is wrong. 2, 2. The first one is right, the other two are wrong. Bizarre. What's in pub key encode? Earl, and then K times 10 bits. K 468. Great. I even read it back out. Oh, I was looking at L. Right. So that it's K. 1312, 1952, and 2592. 2420, yes. 3309, yes. 4627, yes. Okay. The biggest public key is obviously, and the biggest signature size is obviously this. I don't think we need these two anymore. Okay. If len, oh, I guess, do we want to make it, make the parameters also include the key size? Uh, what is happening? Harder to review, but at least we got to do this. Okay, we pull out ch. We make a ring, a vector z, and for each of them we do a bit unpack. And then hint the code. Okay, and we need to implement bit unpack and hint the code. I think hint the code can also return an error. Well, actually it's bit unpack that I don't think can return an error, unless there's not enough signature left, which I guess might as well keep that check. Bit. Oh, we have bit unpack. And it returns just the ring element. Okay. It expects it to be p dot that. Where did we define error? Oh, up there. Okay. Yeah, this is more compact. So we need to hint the code. Code which takes the buffer, each parameters, and returns that. Okay. Wait, why does it take h? No. Later, if we want to save allocations, we're going to do stuff like that, but for now, no. Okay. And while decoding, we need to check if it contains hint bit unpack. Oof. Okay, so how it works. We start our index at 0. For I from 0 to k, if I is less than index, or y, what is y? The input, okay. Let's do that then. For I range p dot k, that plus 1. If limit is less than index or limit is more than that, invalid. Then we put first at index index. For index less than limit. Why is there nesting like this? They could have just said end. What? Yeah, sure. For I from index to W1. Less than that. So 2 minus 1. If y I is different from 0. Yes, this should be uint 8 more than byte, but whatever. Let's see if we can save some of these is in bounds by hoisting this, because it feels like it should manage to elide them. Nope. I mean, come on. We just checked that it's that plus k. Then we range to k. I is up at most k. I don't get it. But it's also not performance sensitive, so... Is index minus 1 always in bounds? Doesn't look like it. Oh, that's the first check. And limit is a must dead. So that's always in bounds. Okay, well, this is always in bound, I think. Maybe this is not? Oh no, this is a byte. It's always in bound. Yeah, it's is inbounding Y, not into H. Okay. I mean, come on, this is less than that, which is the, I guess it could overflow. No, it's unsigned. Anyway, I think we have a SIG decode. We can probably skip straight to verify. Let's put it here. It takes pub, message, context, and signature. I'm wondering if they should be in that order. No, I put them in the order for verify context here. Message, sig, and then context. And also context is a string, which, yep, it probably should be. Let's go change it. Harder to get wrong this way. There. And we made it all the way to the top. So we do sig decode, which gets a ch and all that good stuff. Good. Then we already did this. We already did all this stuff. Now we need to do mu, which we can copy paste from where we do it here. Then we do sample in BL, which we already have up here. Using so we have C, and now we have to do a bunch of entities. So we have to entity C, which we've already done. Then we have to multiply it we have to entity Z, which we might as well do in sig the code. No, we're going to need to check stuff on it anyway. So, no. I'm tempted to put the checks in signature decoding, but it will be easier to, like the check, like this one, but it would be easier to review if it's in the same place as in the spec. So let's not give in to that. So we need to get a Z hat. Boom. And then we need to do AZ Okay, and at the end, so W is expected to be of size the same as T1. So, okay. 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 So for every element, we have to transform the matrix by a vector, which we have code doing that here. So we go through the result and we poly add. All right, well, that's Y, but here we do it with Z, but it's the same. We need to entity Z because we've pre-entitied it, which is necessary because we use it multiple times. Wait, did I just see a performance bug up where I copied this from? Are we doing the entity too many times? Where did I just copy this from? Yeah. We're doing the entity of this every time we arrange for every value of I, but there's absolutely no need. Yep. I keep making these mistakes. Okay. But this is only the first part. Then for each of them, we need to subtract the product um, of C by T1. Yeah. So let's keep the same style as we did here, where we hoist things. Or maybe here, yeah. So let's hoist T1 up here. Actually, let's bring it down here. And add a okay, the subtraction of the product of that and that. I think this is right now. Okay, so we have our W approx. W1, oh, we're so close, but there's use hint, which I remember was sort of a pain. Let's do that. And then the rest we already have code for, so we're so close. So use hint. Use hint takes each value of H and W and actually each coefficient, okay. And it applies the high bits of the compose modulo. Ugh. Ah, that's gonna be annoying. Right, so how did we implement the compose? We have a separate high bits and low bits. Which we're using where? High bits we're using in W1 encode. Which is probably redundant to redo high bits there. And instead, low bits we use in checking the bound, which is not a thing we're gonna have to do here. Let's peek at boring SSL. Use hint. Ah, okay. The mod is just a if. Fair enough. And they call the compose. Yeah. Okay, so they have a separate high bits and the compose calls high bits. That's smart because low bits needs high bits essentially, so might as well do the compose. Well, high bits, you can save time by only doing high bits. Okay. Fair enough. Okay. Let's do the same thing. Oh, I hadn't done it like that because I needed uh the field. The X from Montgomery. I didn't want to do the conversion from Montgomery twice. I think here they operate on things that are already out of Montgomery. Yeah. Let's do the same thing, I guess. We need to int 32 is instead of that. Okay, let's fix the tests. And we need to fix all the places where we use high bits to do from Montgomery. Wait, we didn't fix it here. Wait, what? Oof. Well, I guess it was not incorrect, it was... Okay. The compose is still right. It's really nice to have comprehensive tests, knowing that all of the values are tested. Fuck it. Oops. Okay. Back to our use hint. use hint changes R1 essentially. But it returns only the high bits. And then W1 encode only takes those, or what type does it take? It takes a reading element with a bunch of from Montgomery, which is probably silly. Yeah, bringing it into the Montgomery just to take it out immediately after is pretty silly. But we're gonna have to clean up those types afterwards. For now, let's return the whole thing. Guess this one too is split between 32 and yeah. I think that's right, but I would rather Python it than. $16, yes. We got R1 and R0. And if h equal 1, and R0 is more than 0, R1 plus 1 modulo M. And modulo M is nothing else than, yeah, but I think we can let the compiler figure that out. if h is 1 and r0 is less than, so this is just else, r1 minus 1 plus m. What is r1? R1 is a byte, it's byte. We can't do modulo m if it's... Oh yeah, because it's 16, so yeah, we can. Wait. If it overflows... No, it's fine. If it overflows, then the modulo will take it and will never overflow to 156 because R1 is up to 2 to the... I was gonna say 10, but actually, no? That can't be right. But no, I think this works. And then return R1. Field to Montgomery. Why is he making me do all this stuff? No, it's just R1. Yeah, okay. Let's change the gamma 2 to 88, 44. A modulo here is probably not the most efficient. Which is probably why they do same as us if r more than 0 and 15, yeah. Instead of doing a modulo, they do if r1 is 43, it goes to 0. Okay, so they just made a branch to do that modulo operation. We can probably get to the same place if we figure out the bounds of decompose. Well, this one is easy. What's the bound of her 0? Well, we only need the bound of R1, so... Because it's AND here, so... Well, here... Um... Well, we can test it. We said 43 and 15. Okay. And then using those bounds, we can write a simpler, a faster version here. Okay. We can probably avoid the addition here. Do they avoid it? Yeah. So R1, if it goes negative, it will roll by, yeah. Um, okay. And now we go back to verification and use our new use hint function. Do we need to do the counting the number of ones in H? I don't see it anywhere. Is it in sig the code? It is not. Is it hint bit unpack? Oh no, it's just guaranteed by the encoding. Okay. Yep. For we're about to use W in W1 encode. Okay, this is use hint. So now we have a W1. And we need to do another ch. So h dot reset. We write mu. And then W1 encode. Coefficients. Seed bound. And it's gamma 1 minus bravo. So we need these. Okay. Wait. That's us the other way. this check would make a lot more sense when we're parsing that much early, but let's do things in the order the spec gives us. I think that's it. It's complaining about something. Expected declaration. Oof, I didn't close something. I wonder where. Oh, there's one too many. Okay, let's check if the tests still pass without the signature verification. Then a drum roll, because we might have it. Okay. No, that's not the API. Message, signature context. Okay, and then we can also try a different message. Just to be sure, you know? Because this part here will have a lot more tests to cover all of the branches later, but I just wanted to. Alright, drum roll, did we finish ML-DSA? We did not. 37. So the first one is failing. Let's turn all of these into error F. Yep, they are all failing. Let's make the error message, the errors more useful, I guess. It's the most opaque of the options. Ah, damn it. Could be anything. Shifted left by 13 to Montgomery, assigned, and then NTT. That looks right. Okay, what could it be? How can we break it down? Let's start by ruling out the stupidest possible things, like, is mu the same? So we can print it here. And then we print it in sign. And we try it. It is the same. Wait, is it? Uh, so mu doesn't change between executions. So let's try printing it here instead. Oh, it's sign, verify, verify with the wrong thing. Sign, verify, verify with the wrong thing. Sign, verify, verify with the wrong thing. So it is the same. Well, before it was sign, retry, sign, retry, sign, retry. Verify with the right one, verify with the wrong one. Okay, so the answer is yes. Let's switch this one back to a fatal, so we only see one run. Yep. So that one is the same. Presumably W1 will not be the same. Let's figure out if it's very different or not. These are all the tries. It's completely different. Like nothing in common. Yep, completely different. Okay, so it's not the hints, because the hints barely change it, right? Well, sort of. Wait, does the compose return? No, the compose is not in the Montgomery domain, right? So this is all correct. Hmm. Okay, so it's probably not use hint. Did I just get the matrix multiplications wrong? C can't possibly be wrong because it's sample in B all, which is the exact same thing we do above. Yep. T1 could be wrong, but we looked at it earlier. A can't possibly be wrong. Let's print that hat. Why not? We have it here too, so we might as well check that it's the same. Wait, we don't? Oh, we don't. We can print Z. Which is just a way to check that the signature got round-tripped correctly. We could also write a test for that. Let's do this quick spot check and then we'll do that. Z is the same. Yeah. It would have been surprising if it was that was wrong. Okay, so here we have C, which is right, Z, which is right, A, which is right. And then we do A by Z, and Z is of size L. Yep. And we do the addition in the entity, starting at 0 of the multiplication of A I times L plus J and we get a result. and then we subtract the multiplication of C and T1. That looks right, damn it. Addition and subtraction is component-wise. And then we do the inverse NTT. That looks right to me. I and J. And there's no transposed matrices or anything like that. No, it's just A times Z minus C T1 and CT1 is just scalar by vector, so it's component-wise. And then subtraction is component-wise. This looks right to me. Are we indexing A the same way up here? Yep. I don't see it. Well, we're missing pub key decode, so might as well implement that. And then I'll leave the debugging for when I have a fresher mind. PK decode does what? Easier to just reverse it. Okay, it's taking a row of whatever length that is. It's always 32. Yeah. Actually, we have it here. Yeah, 32. And then a bunch of bit packed stuff. T1 and an error. That looks good. We could also recompute it. Have a function. Yeah, actually, let's do that. Divided by 4. L times n. Too many parentheses. Okay. Better with less repetition here. And we can test the sizes in test constants. Oh, we just hand rolled it in here. Okay, it's 4 at a time, 10 beats each. Okay. Uh, the length of PK is never going to be wrong, but if it makes it feel better. So coefficient 0 is B0 and B1 and 0B 0 0 0 0 0 1 1. I think that works. Yeah. Okay. Oh. This is T1R I plus 0. This is T1 R1 plus 1 plus 2 and plus 3. Okay, this is PK the code. Next, we need a new public key. Oh. Right. Now we need new public key 44. Okay. First we do the code, which checks the length for us. Then we got pub. We copy the raw value. T1. We need to do this same calculation here. And also this. And this way we've populated row P. T1, TR is missing only A. And A is expanded. We can probably clean up some of this stuff, but is sampled by doing that. And this is all the stuff that in verify was in gray. Decoding, expanding, hashing, entitying. Let's try to put them in that order. So that would be expanding, hashing, and entitying. Okay. We might as well they should come out exactly equal, right? Because a public key is just, yeah, they should. Okay. And we turn the fatals back into errors. No, not this one. Not this one, this one. So it will run all of them. We take out the font. Okay. And we try the tests. It will still fail the verification, but everything else should pass. Not identical. That's a weird set. 36, 47, 67. This one. So they're equal in this sense, which, I mean, yes, but 47, which we know, and then 67 is also failing. Ah, well, that's just me being silly. Not identical. Let's figure out why they're not identical. Wait, what? Ah, lol. Let's see, what's different? This will take a minute. God, these things are large. This one is the same, so we delete it. Then this is the same. Then this is the same. This is the same. This is the same. They are the same. Did we compare pointers instead of... Ah! the LLM was even trying to tell us by printing the pointers when doing the printf debugging. Yeah, all right. Parsing works. We'll have to find out what's wrong with the verification, but probably not tonight. Let's commit the verification implementation. And let's mail it as work in progress so I don't lose it. Okay, folks, if no one has any questions or anything, I think this probably pretty much concludes um, the live stream series because we've implemented ML-DSA. We started from, I think, just these first 100 lines that I had already written for the field, which is nothing else than Montgomery. And we wrote everything else live over 4 days. 4 days. And it comes out to 600 lines here and 700 lines here, less than 1500 lines. Our question is, why do I prefer the light theme on the terminal? They actually both switch based on whether it's day or night. I find that having more light keeps me more awake and alert during the day, and after sunset they both switch to dark. Also, for live streaming, I found that people told me that it's easier to watch in light than in dark. Yeah, it even Zotero flips the PDFs at night. I actually kind of like light themes more in general. I find them more readable, but um, I often keep working in the evening after dinner in bed while my partner sleeps, and so I'm like trying to not blind them with with light themes. So terminal and reference and editor are all dark. And then I open a random web page and they start making annoyed sounds. Limit to what you can do. Cool. Well, folks, thank you for keeping me company. I don't plan these, so if you want to join for the next one, which I might do one for the optimizations if it works out, subscribe to the channel to get the notifications from Twitch, or follow on Blue Sky, but I guess that's less timely. Cool. Well, I'll think I'll be off. I'll post on Blue Sky what the bug was when I find it.